Welcome to lecture 76. So, we have started with orbit determination and we will continue with that. So, if you remember last time we have written the state equation. So, state equation it was defined as x tilde dot equal to x 1 dot, x 2 dot, x 3 dot, x 4 dot, and where we have defined x 1, x 2, x 3, x 4, x 5 and x 6. This as x, y, z, x dot, y dot, z dot. So, according to this notation, x 1 dot is equal to x dot, then y dot, z dot, x double dot, y double dot and z double dot. Okay. And finally, we wrote it in a format. So, what we see from this place, x 4 equal to x dot, x 5 equal to y dot and x 6 equal to z dot. So, here we write x 4, x 5, x 6 and then x double dot, the basic equation we had x double dot equal to minus mu by r cube x. This was our basic equation. So, we replace these quantities here, y double dot by minus mu by r cube y and z double dot equal to minus mu by r cube z. And finally, everything we write in terms of x 1 y 1 and so on. X is the quantity here x 1. So, we write here x 1. Similarly, this becomes x 2. And this we can write as f 1, f 2, x tilde, f 3, x tilde, f 4, f 6, x tilde. So, you can see that our state equation it can be written as f times x tilde, where f equal to f 1 to f 6. Okay, we do one more operation here in this place, and also we should note that r square equal to x 1 square plus y 1 square plus x 1 x 2 x 3 square, which comes from x square y square plus z square. Okay, once we have got this, so without currently explaining what I am doing, I just want to linearize this equation. Okay. So, this can be written as from your Taylor series expansion, you can just look into that. So, delta x dot equal to dou f by dou x tilde times delta x tilde, it can be written this way, where f is also a vector and x is also a vector. So, this forms your Jacobian. and this we can write as dou f 1 by dou x 1, dou f 1 by dou x 2, dou x 3, okay. Similarly, the other terms can be written dou f 2 by dou x 1, dou x 2 and so on. Dou f 3 by dou x 1 and the last one will be dou f 6 divided by dou x 1 and here dou f 6 divided by dou f 6 by dou x 6. So, this forms the Jacobian matrix. So, one by one all the 36 elements need to be evaluated. So, let us do few of them I will evaluate and the rest you can check yourself. If we go back, so f 1 is x 4. So, dou f 1 by dou x 4, this becomes and f 1 is x 4. So, this gives you dou f 1 by we are evaluating 1 dou x 1, the first element we are evaluating. So, this is 1. Okay. And these are all independent variables. Okay. Here if you look, once we have casted it in the form of the state space format. So, x 1, x 2, x 3, x 4, x 5, x 6, they are all appearing as independent variable and therefore, this quantity is 0. So, if you look this way, so the quantity from this place to this place, all of them will be 0. You can check for another one, let us say dou f 2 by dou x 2. So, dou by dou x 2 and f 2 is here x 5 and therefore, this also turns out to be 0. Any other element, let us say that and the same way you will have dou f 3 by dou x 3 f 3 is x 6. Okay. So, this quantity also vanishes. Let us evaluate this quantity. So, therefore, we have on the right hand side itself you can write dou f 3 by dou x 1 and f 3 is x 6. So, again this is not a function of x 1 and therefore, this is 0. So, this quantity here the what I am showing from here to here, all the elements will be, these 9 elements will be 0. Okay. So, all of them they are 0. So, this forms a, this is in this format, all the 9 elements here these are 0. It remains to determine the other. So, total 9 we have determined, rest 27 we have to further decide how much what will be their values of those elements. Okay. So, dou f 1, let us first then work out this dou f 1 by dou x 4, dou f 1 by dou x 4 and f 1 as we have written here, this f 1 is nothing but x 4. Okay. This is 4. So, this is 1. Okay. The next element then is dou f 1 by dou x 5. So, dou f 1 by dou x 5 this quantity is 0. So, what you will see if you do this exercise. So, you will see that this quantity from here to here it comes here in this format 1 0 0 0 1 0. We can check for dou f 3 by dou x 6, dou f 3 by dou x 6, dou x 6 and f 3 is from here, this is x 6. So, this quantity is also equal to 1, rest other quantities of the diagonal terms they are 0. Let us say dou f 1 by dou x 6. So, dou f 1 by dou x 6 and f 1 is x 4, from this place we are getting. So, this quantity is again 0. So, this way all the quantities all the diagonal of diagonal terms elements of this partition will be 0. Okay. Rest then we have from here we will have dou f 4 by dou x 1 and so on, and here dou f 4 by dou x 3 and this will go up to dou f 4 by dou x 6. And of course, here then your dou f 5 by dou x 1 it will start from this place, and in this place you will have the element here this particular row, the fifth row, it will the last element, this part will be dou f 5 by dou x 6. So, the fifth row I have not shown here, this is the first element of the fifth row and this is the last element of the fifth row. Okay, so, first we will check for this element dou f 4 by dou x 1. Dou f 4 by dou x 1, and what is f 4? For that we need to go here, you can see the f 4 is this quantity minus mu by r cube x 1. So, minus mu by r cube x 1, but r is itself a function of x 1 square, x 2 square plus x 3 square. So, we need to differentiate this and this both in taking the partial derivatives. Once we differentiate, it will appear like this minus 3 mu by r to the power 4 x 1 plus mu by r cube. Okay. And we can rearrange them to write as 3 mu by r to the power 4 Okay. And here one more term we are missing, which we have to introduce here. Once we are differentiating this r, so also we have to write here dou r by dou x 1, okay, and then plus this quantity mu by r cube dou x 1 by dou x 1 by dou x 1, this will be equal to 0. So, this quantity is missing and that quantity we need to work out from this place. So, 2 times r dou r by dou x 1, this will be equal to 2 times x 1 dou x 1 by dou x 1. So, this is 2 x 1 and therefore, dou r by dou x 1, this gets reduced to x 1 by r, and once we insert here in this place, Okay, this line we directly write first here in this place and thereafter we modify. So, this is minus minus plus 3 mu by r to the power 4 3 mu by r to the power 4 x 1 times dou r by dou x 1 is x 1 by r and minus this becomes mu by r cube. This is 3 mu by r to the power 5 x 1 square minus mu by r cube. So, this is what we get as the fourth row first element. And this way we can find out all the elements which are involved from this place to this place. There are 9 elements here and all these 9 elements can be evaluated. So, on the next page I will summarize this, and if you calculate this part, okay, dou f 6 by dou x 6. So, this also we need to check. F 6 is okay, a few elements we will check and thereafter we will come to this part. Dou f 4, here the fourth row second element, this will be dou f 4 by dou x 2, dou f 4 by dou x 2. The quantity f 4 is minus mu by r cube x 1 minus mu by r cube x 1. So, we can see that the x 2 is here and x 1 is here. Okay, so, x 1 is not a function of x 2, therefore, we did not differentiate the second part and we will get here minus minus plus mu by r to the power 4 and dou r by dou x 2, and 3 will appear here. So, this is mu by r to the power 4 and times x 1 we have to write here, dou r by dou x 2, this quantity will be x 2 by r times x 1. So, this is mu times x 1 x 2 divided by r to the power 5. In the same way, you will have dou f 4 by dou x 3 equal to mu times f 4, naturally it contains x 1. So, x 1 will appear here, and because of this x 3 and differentiation of r with respect to x 3, we get here term x 3 r to the power 5. So, this way you will be able to complete all the terms. Now, the only term that we are left with is here in this row dou f 4 by dou x 5. this we have to work out, this particular partition. Okay. Yeah. Similarly, in the sixth row, the last row, this will be dou f 6 divided by dou x x 1 x 2. No, this is up to only 3. This is up to 3 here x 3, and here it starts with 4, and then dou f 4 by dou x 5. Similarly, here dou f 6 by dou x 4. Here there will be dou f 6 by dou x 3, dou f 6 by dou x 5, and last element dou f 6 by dou x 6. So, I will write it little clearly. Here we will have dou f 5 by dou x 6. Similarly, here in this place we have dou f 5 by dou x 1, and so on. So, this row will continue like this, the fifth row. So, we evaluate this quantity dou x 4 by dou f 4 by dou x 4. Okay. So, we were working with this particular term dou f 4 by dou x 4. Dou f 4 by dou x 4. So, f 4 is this quantity, mu by r cube x 1. So, if you look into this, you take the partial derivative. So, this gives us mu, we can take it outside, mu by x 1 by r cube. So, already we have looked into that r square, this is function of x 1 square, x 1, x 2 and x 3, and therefore, dou r by dou x 4, this quantity will be 0, because nowhere here x 4 comes, there is nowhere x 4 present in this term, thereafter there is nothing, you do not have anything here. So, this quantity gets reduced to 0, and x 1 also dou x 1 by dou x 4, this quantity is 0, because x 1 is not a function of x 4. So, this way you will see that this quantity is equal to 0. So, all other terms in that matrix, that turns out to be 0. So, finally, we can write this as the Jacobian matrix, which we were writing this matrix. Let us say this Jacobian matrix we write as A. Okay. So, this matrix can be written as A equal to 0 0 0 0 0 and other elements we have to enter here. So, dou f by dou f 4 by dou x 1 already we have evaluated, dou f 4 by dou x 1 is the quantity we have written here. Okay. So, this is mu times 3 x 1 square by r to the power 5 minus 1 by r cube. This is the first element. The second element dou f 4 by dou x 2 is mu times, we won't be able to adjust here, let me try. So, we will go on the next page. The first element we have 3 mu times 3 mu times 3 x 1 square divided by r to the power 5 minus 1 by r cube. The second element we are taking from this place, this particular element which is coming here, dou f 4 by dou x 2. So, this quantity is mu x 1 x 2 divided by r to the power 5, mu x 1 x 2 divided by r to the power 5. The next element we have written mu x 1 x 3 divided by r to the power 5. And if you further differentiate, you will get the other terms also, and it will appear like this: 3 x 2 square by r to the power 5. You can check the other terms. This 3 is missing here. So, we need to place this 3. Similarly, the 3 is missing here in this place. So, 3 is missing here, we place 3 in all these places. So, 3 mu, now this will be x 2 x 3. You can see this is off diagonal terms, they are symmetric. Okay, so, this constitutes your 9 into 9, 18 elements, and rest of the elements are 1 0 0 0 1 0, and here in this place okay. So, this is your A, the Jacobian matrix, which we have got after linearizing the equation x tilde dot equal to f x tilde. And this term briefly also it can be written as mu by r to the power 5 3 x 1 square minus r square. So, this way also we can write, it is not a problem. Okay. Once we have determined this Jacobian matrix, so delta x dot, then we can write as A times delta x tilde. Delta x tilde dot equal to A times delta x tilde, which we have got after linearizing this equation x dot equal to f x tilde, where A is nothing but dou f by dou f, which is a vector itself, and x tilde. And this can be solved. So, solution to this from your basic mathematics, or those who have done the control course, they must be aware of. This is A times t minus t 0, or from your differential equation this can be written this way, where t equal to t 0, this is the initial time and delta x tilde is the initial state as appearing in this equation. Okay. And this quantity is written as phi t t 0 and we insert, if we insert here in this place, so we get phi dot t t 0, this is a constant, this is the initial condition, and this part insert here on the right hand side. So, this gets reduced to a times phi t t 0 delta x tilde 0. Since delta x tilde 0 is not equal to 0 and therefore, phi t t 0, this quantity equal to a times phi t t 0, where phi t t 0, this is your transition matrix. So, any controls book you look into the state space method, state space control, and there you will find what this transition matrix properties are. So, I will just state that phi t t 0, this equal to I, which is the I is the identity matrix, and therefore, this phi t t 0 at different instant of time, it can be evaluated by integrating this. So, this quantity will be a phi t t 0 t 0 to t dt. Okay, so, you are starting with this initial value, you can go on to keep on integrating and step by step you can get this, or either this transition matrix, it is also written as this equal to e to the power a t minus t 0. So, this is I times a times t minus t 0 plus a square by 2 factorial, where A is a matrix, remember this is the Jacobian matrix, t minus t 0 square a q by 3 factorial t minus t 0 whole cube and up to infinity. Okay. So, this method of evaluating the transition matrix at different instant of time, it is a costly because you have to keep multiplying the matrices one after other, okay. And the more term you take, the more accurate this will be. Here in this case, once you are starting with the value of the a and you have this phi t t 0 t 0 t 0 initially right in the beginning equal to identity matrix. So, you can just keep integrating and you will get this result, the transition matrix at different instant of time, and this is comma, not 1, these are comma. Okay, so, this way your transition matrix is evaluated, and why we are doing this, it will be shortly visible to you. So, we stop here and we will continue with this topic in the next lecture.